Hello. So we're starting from this point where we have an isotherm, and we're trying to find what is the P alpha, and therefore what is the V alpha and the V alpha prime for the coexistence line, this line that connects this point to this point for the two final volumes. One of them corresponds to the liquid and one of them corresponds to the vapor phase. So the question is, how do we find P alpha such that the Gibbs free energies of the two partitions, the two phases, are equal? We'll start with the simplest version of the differential Gibbs energy equation, which is the small change in Gibbs free energy is equal to the small change in the pressure minus S times the small change in temperature. But remember, we're on an isotherm. So this term is gone. So then we only have to worry about calculating Gibbs free energy from V under bar dP, which luckily we have equations of state for. Problem solved, right? Should be really easy. Well, it's hard. It's actually really hard. So delta G, that's dG. So delta G between two pressures on this chart is going to be calculatable. It's equal to the difference between P1 and P2. This is just general of V dP. This tells you the change in the Gibbs free energy going from one pressure to another. So for a given cubic or other, can't do this with the ideal gas equation of state because you'll never have more than one value for pressure for any given, or more than one value for volume for any given pressure. We can use this information and this approach by taking a cubic equation of state and plugging it in to this integral equation. So the way that this is done, let's just call this method 1. Okay, so P alpha is somewhere on the interval between PA and PB. And then what you do is you iterate. Oh man, I'm having a spelling fail day. Iterate until G under bar V minus G under bar L is equal to 0, until the Gibbs free energies of those two phases equal to 0. So what does this look like on this graph? This is going to be GV minus GL equals 0, equals the integral from P alpha up to PA V dP plus the integral from PA to PB of V under bar dP plus the integral from PB to P alpha V under bar dP. So, what does that look like? If you look at a graph, we have to recall, we have our equations of state, our pressure as a function of volume, but we need to have volume as a function of pressure to stick the equation in this integral. So graphically, the best way to show this is by, for instance, our initial graph, looks like this. We have this line with this squiggle. Ultimately, graphically, this means you find a P alpha such that the areas here, 1 and 2, the areas of 1 equals 2. But really, when you're doing the integral, it's so different than the other types of integrals that you're used to. Because if you flip this around to somehow get p as how it depends on v, it's no longer a function, because p, if p was the independent variable, the whole graph would look like this. We'd be flipping this initial graph on its head. And so then your P alpha term would be somewhere here. You'd have PB over here and PA over here. So this is why this calculation is a challenge, because you're trying to integrate something that's not really a function. So you break this integral up and you have to add and subtract pieces. Plus you have to somehow solve for where this crosses in all these places here. There's no way to get a function for p, because it's not a function. P is, for v. V is not a function of p. It's the other way around. And so flipping this in this way suddenly gives you a graph that you really can't just integrate using the rules that you're used to. But anyways, you could do this, with a computer. And so I'm just going to list the rules here. In the end, this is how we're not going to do it. We're going to do something simpler. But rules to construct your own PV diagram. So, 1, use stability. This is mechanical stability criteria. Del P, del V at constant temperature is less than 0. That's something you know. That's that region we talked about. That's right here with this exploding region. We know that's not possible. 2, in your simulation, is also an obvious one, but require that in your two partitions, temperature 1 is equal to temperature 2. And pressure 1 is equal to pressure 2. So draw a line straight across. If this finds the coexistence line. 3, move line up and down until your calculation for the Gibbs free energies, the per molar Gibbs free energies are equal. Conceptually, this is the process. In practice, we use something else entirely. In practice, we make some mods to make this doable. And there is no way to get around it. There is no way to have a thermodynamics course that has vapor and liquid equilibrium without talking about the item that is the butt of jokes in thermodynamics. And it's a frightening thing that even appears in pop literature once in a while. We have to tackle this thing called fugacity. And that is what will come on the following day of material for this course. Everyone stay healthy, stay safe, and practice your thermo. It gets more fun every day. Bye.